Okay, so we're going to talk about a few more items. In particular, I want to skip past this and talk about typed languages and the terms. The terms I want to use are statically typed and dynamically typed. Okay, so a statically typed language is like Java. At compile time, the compiler knows for every variable, for every piece of information it's going to be moving around, it knows what the type is. And in fact, when you compile your program, it first checks for syntax errors. Then it runs, Java C runs a type checker. And it makes sure that, hey, this function here is supposed to be passed a string. Is it really passed a string? And it verifies that because you've declared what types everything was in the code that calls that function. And hey, that function is returning a double. The place where are you using it? Are you using it in a place where a double is expected? Yeah, so it checks all these things. This has the advantage that at runtime, it doesn't need to check these things. It knows that when you call that function at runtime, that you're going to be passing it a string, and it doesn't need to check it at that time. And likewise, it knows that that function returning a double, you're going to use it in a place where a double should be, and so it doesn't actually have to check that the bit pattern is the right type, or it doesn't even, actually it's a little bit better. The bits moved around on the machine, the 32 or 64 bits, say it needs to know whether something is a double or an int. Well, either way, it's just 32 bits, right? Is that 32 bits a float, or is that 32 bits an int? You can't tell by looking at those 32 bits. There are just different numbers depending on how you choose to interpret them. But that's okay, because at runtime it doesn't need to. It knows that, hey, these 32 bits are an int, these 32 bits are a float, and it's using them in the right way. Why? Perhaps the programmer was required to annotate their program with all the different types. That's what you do in Java. You have to specify the type of everything. It runs, when you compile, Java C runs a proof to make sure that all the types really do line up. Then at runtime, it's just moving bit patterns around, and it doesn't need to know the types. Compare that with a dynamically typed language, like Racket or JavaScript. So the language still knows the type of every value, but you don't need to declare them in your program. And in fact, at compile time, the computer does not know what type a certain variable is going to be holding, or what type is returned by a function. It maybe doesn't even know that in a dynamically typed language. Well, gosh, it still knows that there's different types, and it still wants to catch any type errors. If you try passing a string to a function that expects or an int to a function that expects a double, gosh, the bit patterns might need to be converted at the very least, if not actually raise an error. So how does that happen in dynamically typed language? They tag each bit of data. So look at 32 bits as an int or double. Really, it might not be 32 bits. Maybe they use 3 bits as a tag. And the remaining bits represent either an int or a float. So out of 32 bits, maybe the top 3 bits are 000 means int, because that's one of the most common data types, okay? And 001 means float. And 00 or 010 might mean, some other common data type, a Boolean. There might be, 100 might mean, hey, this is a arbitrary precision integer that's to be treated as a linked list, and part of these other bits are memory addresses that are chaining along a linked list or something. Or the memory right after the 32 bits is going to be an address of where to look for the next cell in a linked list. So the language is going to be doing more things, and it's going to be doing them at runtime. When you call a function, when you call square root, it's going to double check, hey, is this really a numeric type going in? If it's an int going in, it might call another function that turns that int into a float. If that bit pattern indicates that it's a string or something else, it might give an error at runtime. So, we have a trade-off. We don't force the programmer to annotate their program with all the types they're using. Say, this is going to hold an int, this function has to take in this and return one of those. We still like doing that. Union types that we've been dealing with are a good example. It's hard to do a union type in Java because yeah, Java suddenly says, well, gosh, this function might be returning an int or a Boolean. I don't know how to treat that bit pattern. Well, if you have extra tag bits at runtime inside the runtime system, then that's not an issue. What's the trade-off? Well, I guess your 32 bits that you're using for an int or a float, really you're only using maybe 29 of those as actual data. And when you send these bit patterns off to the hardware to add, there's hardware circuits that will add floating point numbers. You might have to mask out some of those bits or change some of those, fiddle those little bits before you send it down to the metal to get added by the ALU circuit on your computer. So less work, less burden on the programmer to declare their types, more work on the runtime system to make sure a type error doesn't happen, that the right types are passed as expected. Okay, I should mention there's an in-between. So statically typed, compile time, the compiler knows the types of every single declared name. That can be the programmer annotating the program, or it could be the compiler sort of inferring the types. So a very limited example is in C#. You can say var n gets 5. You don't need to say that n is an int. It will figure out that n is an int because you're initializing it with 5. In Java 8 or so, they introduced the diamond operator when you're declaring a variable and initializing it in the same line, and you're using a parameterized type like linked list angle bracket integer. You can leave off this thing inside the angle brackets a little in one of those two cases when you're declaring and initializing the same line, and it will figure out for you what you mean. That's a little bit of type inference, not a very profound type inference perhaps. ML and Haskell are more interesting examples. They are statically typed languages, but you don't need to specify your types at all if you don't want. So you can go ahead and write your program, don't specify types at all, and then the compiler at compile time will try to infer, well, I see here you assign an int into it, and over here you assign an int into it, so this really must be holding an int, or maybe here you assign an int to it, here you assign a double, it's going to be a super type number or something like that. And it goes and tries to infer things. That's pretty cool. ML is neat in doing that. That's one of ML's big contributions is type inference. One drawback in experience, if you do have an error in your program, your n is supposed to be an int, you assign an int over here, you assign an int over there, over somewhere way off in some other place, you assign the result of calling a function. That function can return an int or a string. Gosh, ML will sort of reverse engineer, will assume that that's right and say, hey, the type of n is int or string, and now when you pass off n to square root, it will give you a type error saying, hey, you can't pass an int or a string to square root. It has to be numeric. And that place where you get the error might be far unrelated from the place where you assigned n something that might be an int or a string. So the type system may not give the correct human intuition about where the error was. The error may have been over here, but it reports it way over here, and it can be hard to trace through the error messages. So that's, again, one of the trade-offs. Both ML and Haskell, you don't need to declare any types. You can declare types as hints, okay? And there might be occasional places where the compiler says, oh, I can't tell what's going on here. You need to give me a few hints about what type some of these variables are. Oh, okay, now that you nailed down this one type, now I can figure out what's going on. Otherwise, it was ambiguous. So we're not going to worry about those things, but it's an interesting approach. We're used to a world where either we're in Java and we're statically typed and we declare everything, or we're in JavaScript and it's the Wild West and we don't declare any types except maybe in comments, and we just sort of hope everything works, and we might get an error at runtime. Okay, I want to, I'll mention a few other terms here. Duck typing, it's a cute term people use. Duck typing, JavaScript is the big poster child for this one. When you have an object, it doesn't really care about the type. If you call a toString method on some object, as long as that object has some method defined as toString, called toString, it will call it, and it doesn't really care how it got that method or that field. Or if you have an object has a method called speak and you call it, it doesn't really care that, oh, well, yeah, it has a speak method because it was inheriting from a class animal, whereas, you know, maybe it was, no, this was a artificial intelligence object and it had a method speak for very different reasons. It just says, hey, you're calling speak, it has a method speak, yeah, let's do it. Which actually loses some of the things you try to get in when you're declaring types, the static type system. On the other hand, it gives you a lot of flexibility. The JavaScript people who like that really tend to like that. Yeah, I don't need to worry about classes and hierarchies. I just make sure it has the right methods for the things I actually end up calling on it, and that's good enough. Okay. An untyped language. Now, I want to specify or distinguish untyped from dynamically typed. Sometimes people say, oh, JavaScript or Racket are untyped languages because you don't declare them like you do in Java. Well, no, they know about type error. If you try calling square root and you pass it a string, you'll get a type error, okay? As opposed to untyped would be an assembly language where it just takes the bit patterns and mashes them together and does something with them, okay? Which brings up the related concept of type safe. If you have a type error in your program, is it caught and maybe your program crashes, or maybe it's caught at compile time, or does your program proceed as if everything were hunky-dory when really something has gone horrendously wrong? If it can proceed when something has gone wrong, it is not type safe. So assembly is not type safe. If you have a bit pattern you thought was an int and you pass it to a function that expected to be getting a bit pattern that was a string or a string pointer, yeah, heaven help you. If you're lucky, your program will crash. If you're unlucky, it will keep on running and give awful results. So C is an example. Sometimes people say, oh, C is like Java, I declare all my types. The one little caveat is C lets you cast whenever you want. And what does casting do in C? Casting means go ahead and ignore anything the type checker was going to warn you about. Something's not compiling because it says, hey, I think this is the wrong type. And you're like, well, I know it's really that type after all. I'll cast it. All that does in C is perhaps turn off the type checking. So you can have type errors in your C program. I should mention that in Java, type casting, really I guess in C and Java, there's two types of casting. One is casting primitive types, casting an int to a double. That's really just shorthand for calling convert int to double. And that just sort of rearranges the bits. Oh yeah, in the int 17, I'm going to give you the bit pattern for the floating point 17.000. And it's really, I think it should be just called a conversion function like int to double. However, in Java, when you do a cast of an object, okay, say, hey, I'm doing some GUI stuff, I get back an event listener, and it can be any type of event listener, or I look up the source of an event, and I get an event source. I might know in my program the only event sources were JButtons, okay? So I might need to cast, and I want to call one of the methods on this event source. I'm like, oh yeah, call this method, and some methods particular to JButtons. Java, when you compile, says a type error. Whoa, you have an event source here, which could be any event source I don't know is a JButton, and you want to say, hey, I'm going to cast it. This thing is a JButton. I know that. You don't know that, compiler, because you're not looking at the whole program and not reasoning as well as I can. But I know it's a JButton. Inserting the cast in Java does not do what it does in C. In C, that would just sort of ignore the type error and let the program proceed. In Java, a typecast like that does a runtime type check of extra tag bits, okay, that objects have, and it really does check the runtime type of that object at runtime, and will fail if it's not a JButton. It will cause an exception. So casting looks similar in both C and Java, but theoretically there's this difference. One lets errors proceed and the other one doesn't. Although one thing to know is whenever you cast in Java, you are giving up your guarantees, your runtime guarantees that you don't have any type errors in your program, and you're sort of falling back, and even though you had to declare all your types, you're still having to further do type checking at runtime and losing the advantage of having declared all your types. So, okay, sometimes Java's library makes it kind of necessary. Okay, so again, untyped, people will sometimes use the term strongly typed or weakly typed. And sometimes when they say strongly typed or weakly typed, what they really mean is statically typed or dynamically typed. Misleading terms. I prefer statically typed, dynamically typed. Those are both very clear. Because another way people use strongly typed and weakly typed is meaning, are there a lot of implicit conversions? Okay, so consider in Java, math.square root of 16, the language helps you out. It says, hey, square root expects a double. You're giving an int. I'm going to go ahead and cast 16. I'm going to do that, cast that, convert into double, int bit pattern to double bit pattern, and then pass it to square root. Okay. And it just sort of does, that's an implicit conversion it's doing for you. Okay. Or in Java or PHP, let's take the string 50 plus 60. What does that give you? In Java, can you think about what it gives you in Java? It gives you the string 5060. Yeah. In PHP, it ends up giving you 110. Why? PHP is doing some implicit conversions in a different way from how Java does them. Also in PHP, plus is only for numbers and not for strings at all. So, yeah, so languages sometimes do these conversions. Java tends to do a few conversions for you in places where it helps. PHP, it's like the kid who's trying to be helpful, but just ends up getting in your way more often. PHP, it does so many type conversions for you, implicit type conversions, it will often get you in trouble. It will do things that were an error in your program, and it fixes them by doing some weird conversion that was totally unexpected. So, it's not clear to what degree implicit conversions by the compiler are helpful to programmers and how much they hinder you. But what I'm getting at here is strongly typed or weakly typed. Sometimes people mean that to talk about how permissive the language is in terms of implicit conversions. So I'm going to try to avoid using strongly typed and weakly typed. I'll say statically or dynamically typed, and I'll talk about a lot of implicit conversions or not, and leave it at that. So, okay. And I'll come back and cover one more slide later.